Today we will discuss differentiability and chain rule. So let us start. The derivative of function f is given by f dash x is equal to limit h tends to 0 fx plus h minus fx by h, wherever the limit exists. What does it mean? It means left hand limit, that is limit h tends to 0 minus fx plus h minus fx by h, and right hand limit, that is limit h tends to 0 plus fx plus h minus fx by h are equal. F dash x d by dx of fx dy by dx and y dash are same. These are other notations of derivative of f. Also, the derivative of f at c in its domain the derivative of f at c in its domain is given by f dash c, which is equal to limit h tends to 0 f c plus h minus fc by h. We replace x by c. Now let us do a theorem. Before that, let me recall the algebra of derivatives. We have studied that the derivative of sum of two functions is the sum of their derivatives. The derivative of the difference of two functions is the difference of their derivatives. The derivative of product of any two functions is equal to first function into derivative of second function plus second function into derivative of first function. U divided by b whole dash is denominator has v square and the numerator has u dash v minus v dash u, wherever v is not equal to 0. We have also studied the derivative of x to the power n is nx to the power n minus 1. The derivative of sin x is cos x is minus sin x, tan x is sec square x, cot x is minus cosec square x, sec x is sec x into tan x, cosec x is minus cosec x into cot x. So the theorem is if a function is differentiable at a point C, then it is also continuous at that point. Let us prove it. Since f is differentiable at a point C, therefore limit h tends to 0, fc plus h minus fc by h is equal to f dash c. This implies that limit x tends to c, fx minus fc by x minus c is equal to f dash c, where x is equal to c plus h. Then h tends to 0 implies x tends to c. I have just replaced h. So here h is equal to x minus c. This is our equation 1. We have to prove that f is continuous, means its limiting value at c is equal to fc. So if x is not equal to c, then fx minus fc, this is equal to fx minus fc by x minus c into x minus c. This implies the limit x tends to c, fx minus fc is equal to limit x tends to c, fx minus fc by x minus c into x minus c. This implies that limit x tends to c, fx minus fc, because this is constant and it is unaffected from limit. Here we have limit x tends to c, fx minus fc by x minus c, limit x tends to c, x minus c. Here we have limit x tends to c fx minus fc. This is f dash c from equation 1. This is 0. So our RHS is 0. From here we can write limit x tends to c, fx is equal to fc. This implies that f is continuous. Hence the result. On the basis of this theorem, we can say that every differentiable function is continuous. But its converse, every continuous function is differentiable, is not true. Let us give a counter example. For fx is equal to mod x at x is equal to 0. It is continuous. We have already shown in continuity. Now we have to check its differentiability. So we write left hand derivative LHD, which is equal to limit h tends to 0 minus f c plus h minus fc by h. Here c is 0. So limit h tends to 0 minus, here we have to check differentiability at x is equal to 0. So c is f0 plus h minus f0 by h. Here h tends to 0 minus means h is negative. So we have fh f0 here, fx is mod x, so mod 0 is 0. This is limit h tends to 0 fh. Here h is negative, so if x is negative, we know that fx is minus x, so minus h by h. This is minus 1. Is that clear? Here h is negative because h tends to 0 from left side, so fh is minus h, because we know that if x is negative, mod x is minus x. Now right hand derivative, RHD. This is limit h tends to 0 plus fc plus h minus fc by h. Limit h tends to 0 plus f0 plus h minus f0 by h. Limit h tends to 0 plus fh minus f0 is 0 by h. Here h is positive because h tends to 0 from right side, so fh is h, because if x is positive, mod x is x, so h minus h. H minus h by h, this is 1. So we see LHD, which is minus 1, RHD, which is 1, are not equal. That's why mod x, fx is equal to mod x is not differentiable at x is equal to 0. Graphical interpretation. This is our graph of mod x, and we see that it has corner at x is equal to 0. From here we can say if the graph of a function has corner at a point, then that function will be non-differentiable at that point. Chain rule. Let f be a real valued function. Suppose that f is composite of u and v, where here t is equal to ux and both dt by dx and dv by dt exist. Dt by dx and dv by dt exist. Then df by dx can be written as dv by dt into dt by dx. Here only two functions are taken, but it may be extended for more than two functions. Let us do a problem. Find the derivative of sin x square. See here, this sin x square is, what is it read? Sin of x square. So it is the function of x square. So we write this is the way to write it, to apply chain rule. Now here d of sin x square, we know that the dc of sin x is cos x, so cos x square. Here its dc will be 2x. You know that x to the power n dc is n x to the power n minus 1. So we have 2x cos x square. Find the derivative of sin ax plus b by cos cx plus d. D by dx of sin ax plus b by cos cx plus d. You know that this is u, this is b, and its dc will be given by, here we write cos square cx plus d. Here we write cos cx plus d, and dc of sin ax plus b minus sin ax plus b dc of cos cx plus d. Now here we apply chain rule, cos cx plus d. Sin of x plus b, this is the function of ax plus b. So we write here ax plus b by d ax plus b, and dx plus b will be written here. Here sin ax plus b. Here we write cos cx plus d, which is the function of cx plus d, and cx plus d will be function of x. Now its dc is cos ax plus b, and its dc is ax plus b, dc is a. Here its dc is minus sin cx plus d, and here cx plus d dc is c, because you know that the dc of constant is 0, here d is constant, and the dc of cx is c into dx by dx. Cos square cx plus cos cx plus d. The dc of sin ax plus b is cos ax plus b, and the dc of ax plus b is a, minus sin ax plus b, and the dc of cos cx plus d is minus sin, so it becomes minus sin cx plus d, and the dc of cx plus d is c. Now it can be rearranged as a cos ax plus b cos cx plus d plus c sin ax plus b sin cx plus d divided by cos square cx plus d. It can further evaluated. Here a cos ax plus b, cos cx plus d is cancelled with 1 cos cx plus d, then we have 1 by cos cx plus d. This is sec cx plus d. This plus here c sin ax plus b, sin cx plus d by 1 cos cx plus d is tan cx plus d, and another cos cx plus d, 1 by cos cx plus d is sec cx plus d. Let's do next question. Differentiate to a square root of cot x square with respect to x. we have to find this one. See here, 2 is constant, so it is taken outside. This one. Now can you think of which this is a function? Here a square root of cot x square. So firstly a square root occurs. So this is a function of cot x square. Now this is cot of x square. So this is a function of x square. Now here x square is function of x. Once again, here this is a square root of cot of x square. So firstly a square root occurs. So a square root of after of cot x square occurs. So we write cot x square. Now cot square x is written here. Here cot of x square after of x square occurs. So we write x square here. Here dx square, and it is the function of x. Now proceed. 2. Here a square root of cot x square. This is x to the power n. N is 1 by 2. So 1 by 2 n minus 1. Right? Now this one, dc of cot x square. This is minus cosec square x square. dc of x square is 2x. Here 2 is cancelled. Here minus 1 by 2 occur. So we can write 2x minus 2x cosec square x square divided by square root of cot x square. Now it can be further simplified. It can be written as 2x sine square x square. Here this is cos x square by sine x square. Now this is minus 2x, and here you can write sine x square, and here a square root of sine x square. Here 1 sine x, so we get sine x square cos x square. Now this is minus 2x sine x square. Here sine x square cos x square. We can multiply with root 2 above and below. So this is minus 2 root 2 x divided by, here we know that 2 sine theta into cos theta is sine 2 theta. Differentiate cos x cube into sine square x to the power 5 with respect to x. Solution. Here there are two functions whose product is given. So we know that the dc of the product of two function is the first function into dc of second function plus second function into dc of first function. Now see, here cos x cube. Now d sine square of x to the power 5. Here this is a function of sine x to the power 5, and sine of x to the power 5 is function of x to the power 5. Again x to the power 5 is function of x. plus sine square x to the power 5. Here this is a function of cos x cube is the function of x cube. So and x cube is the function of x. Here cos x cube. Now x to the power n. Here x is sine x to the power 5. So we write 2 sine x to the power 5 n x to the power n minus 1. 2 minus 1 is 1 here. Now here dc of sine x is cos x, and here x to the power n is 5x to the power 4 plus sine square x to the power 5. dc of cos x is minus sine, and this is x to the power n. Now rearranging them, 5 to the 10, x to the power 4 sine x to the power 5 cos x to the power 5 cos x cube minus 3x square sine x cube sine square x to the power 5. Here the question is, prove that the function f given by fx is equal to mod of x minus 1, x belongs to R, is not differentiable at x is equal to 1. Let us write fx, which is mod x minus 1. This can be written as minus x minus 1, that is minus x plus 1 if x is less than 1. You can see if you take x is less than 1, then this function is, suppose 0 minus 1, this function is negative. That's why we multiply this with minus sign. And x minus 1 if x is greater than or equal to 1. Now we take LHD and RHD. LHD is equal to limit h tends to 0 minus fc plus h minus fc by h. C plus h minus c is h. So here written h. This is the way to remember. Limit h tends to 0 minus. Here we write c is 1. 1 plus h minus 1. f1. Here h is negative. So 1 minus h is less than 1. Then we take minus x plus 1. And f1 is x minus 1. So 1 minus 1. Here h. Now this is 0 minus 1 plus 1. This gives us limit h tends to 0 minus minus h by h. Here we have minus 1. This is cancelled and we have minus 1. Its the limit is. Now RHD. Limit h tends to 0 plus fc plus h minus fc by h. Here c is 1, so limit h tends to 0 plus f1 plus h minus f1 by h. Limit h tends to, see here h is positive, so 1 plus h is more than 1, and then the value of the function is x minus 1, that is 1 plus h x minus 1, and f1 is x minus 1, so 1 minus 1 by h. Here we see limit h tends to 0 plus 1 minus 1 is 0, here 0, h by h. This gives us 1. So this is 1. You can see LHD is minus 1 and RHD is 1. Clearly LHD is not equal to RHD. This implies that f is not differentiable at x is equal to 1. Prove that the greatest integer function defined by fx is equal to greatest integer x, where 0 is less than x is less than 3, is not differentiable at x is equal to 1. Solution: fx is equal to greatest integer x. Here x is defined within 0 is less than x is less than 3. So when 0 is less than x is less than 1, then the value of greatest integer x will be 0. You know that greatest integer x is the greatest integer less than or equal to x. Here x is below between 0 and 1. That's why greatest integer less than x will be 0, and another condition will be this one. For this, greatest integer will be 1. Now we have to take LHD and RHD. So LHD, limit h tends to 0 minus f c plus h minus fc by h. Here c is 1. So 1 plus h minus f1 by h. Here h is negative. So 1 plus h is less than 1, and its greatest integer will be 0. Greatest integer of 1 will be 1 by h. Here we have minus 1 by h. Limit h tends to 0 minus 1 by h. H is negative and nearer to 0. So if we divide minus 1 with a very small negative value, then we get infinity. Now RHD, limit h tends to 0 plus fc plus h minus fc by h. This is equal to limit h tends to 0 plus f1 plus h minus f1 by h. Here h is positive, very small positive value. So 1 plus h is more than 1, and for that greatest integer will be 1. f1 is 0. f1 is 1. Greatest integer of 1 is 1 by h. So 0 by h is 0 by any h is a very small positive value, so this gives us 0. Here 1 plus h is more than 1, and for more than 1 greatest integer will be 1. 1 minus f1 is 1, so 0 by h. H is a very small positive value, this gives us 0. So we see LHD is infinity and RHD which are different. Clearly LHD is not equal to RHD. Hence f is not differentiable at x is equal to 1. That's all in differentiability.